Good evening. Good evening. Am I audible? Hello. Thank you. Thank you. We'll wait for others to join in. We'll wait for another 5 or 6 minutes. Okay. Now the time is 8:06. We have 5 students. Shall we wait for another few minutes, or shall we start? Okay. Now today we are moving into a new section. We are going to first study about flood runoffs. Then after that we are going to study about a very important tool called hydrographs. Now I think we have briefly touched about the runoff. Now today we are going to talk little bit detail about the runoff. Now when rainfall falls onto the ground, part of it will be evaporated, evapotranspirated, part of it will be infiltrated, and the section of the water that is infiltrated will go in parallel to the ground surface, which is called the through flow. Then part of it will reach the water table beneath. Now water table is a pool of water stagnant on the confined aquifer. Now we will be talking about confined aquifers and unconfined aquifers in underground water hydrology. Now the balance amount will be running on the surface. So that is called overland flow or runoff. Now it will reach a water body at a certain time. So the runoff that is taking place out of a catchment can be estimated. Now, for the proper technical definition, let's read what runoff means. Runoff means the draining of flow of precipitation from a catchment area through a surface channel. It thus represents the output from the catchment in a given unit of time. Now there are factors that need to be fulfilled before creating the runoff. So the evapotranspiration, then infiltration capacity, initial losses has to be gained. Now let us briefly talk about the definitions. Now we were talking about several technical terms in the previous slide, and let us talk about these definitions. Now overland flow. Now overland flow is defined as the excess precipitation moves over the land surfaces to reach small canals. So this is what we call overland flow. Now the surface runoff is when overland flow reaches end of catchment. It is called the surface runoff of the catchment. Now we were talking about the catchment and catchment runoff in the previous lesson. So surface runoff is the runoff from the surface at the outlet of the catchment. Through flow, a part of precipitation that infiltrates, moves laterally through upper crusts of the soil and returns to the surface at some location. So I have just told you in the using this diagram what the through flow means. Now groundwater flow. Now, the segment of infiltrations that reach deep aquifers, which create long-term water flows for rivers, is known as groundwater flow. Now, when this part of this infiltrated water reaches the ground table, it creates beneath rivers. So, the outflow from the groundwater is called groundwater runoff. Based on the time delay between the precipitation and the runoff is classified into two categories. Now when the precipitation comes, the runoff will not come out of the catchment directly. There is a time lag. So based on the time lag, there are two types. There is something called direct runoff and the base flow. We will be talking about this under the hydrograph. Now let's look at direct runoff and base flow. Now, when a catchment receives water, the natural flow of that catchment is estimated using this equation. Now, this R naught is the observed flow volume in a given time delta t at a terminal site. Now, let's say at an outlet, if you observe the runoff, that is R naught, and I'm going to show you a video of flow measurements for runoff. Now VR has to be deducted. Now VR represents a volume of return flow from irrigation, domestic water supply, and industrial use. Now, if there is irrigation taking place or the domestic water supply, part of the supplied water will come back as a runoff. So that needs to be deducted, because if we embed that in the natural flow, we will call it the yield, and I will give you the equation for yield in the next slide. Now VD is the volume diverted out of the stream for irrigation. Now if somebody is diverting the water from that stream for irrigation, that need to be added. Then the net evaporation losses from the reservoirs on the stream. Now, if there are reservoirs built, so those reservoirs will create evaporation. So that needs to be added, because that is a loss from the natural flow. So if you are going to calculate the natural flow of the stream, that needs to be added. Then Ex is the net export of water from the basin. Now, if somebody is sending water away from the basin, so it is called Ex. Now, delta S represents the change in the storages of volumes of water store bodies. Now, let's say if you have reservoirs or canals that stores water that should be there in the river, that need to be added to calculate the natural flow. So that is how they have created this equation. Now let us talk about the yield. Now here we were talking about Rn, right? Now you can see all others are additions except for the runoff from the irrigation, or the return flow from the irrigation water. But yield is the actual water that you yield out of a catchment. So you have to add VR to RNS. So basically, you need this, you have to move this to the other side. So you will get this equation where R naught is the observed runoff and AB is the abstractions. This includes irrigation, water supply, industrial use, then the storages in the reservoirs in the catchment. Now, I'm going to play you a video that demonstrates how to measure stream flow. Please watch this carefully. Please watch this video.
Hello students, today we are going to discuss the stream flow measurement, specifically the area velocity method for stream flow measurement. So first of all, let us understand what is stream flow. It is simply the discharge that is flowing through a stream. And how to measure it? We have two approaches, direct method and indirect method. Under the direct methods, we have area velocity method, moving boat method, dilution technique, electromagnetic method, and ultrasonic method. Under indirect methods, we have slope area method and few flow measuring structures. In this presentation, we will be focusing only on the area velocity method. In this method, first of all, we have to select a gauging site where we will be measuring the discharge. So this gauging site is selected carefully and it should have a well-defined cross-section which should not vary with time or with season. And that gauging site should be easily accessible throughout the year. As far as possible, the site should have a straight and stable reach in the upstream. And the last one is it should be free from backwater effect. Let us consider this as the cross section of a river. This is the water surface forming the overall cross section of the flow area. We draw a vertical line at a distance, certain distance from the left bank, and this vertical line is called simply vertical. Similarly, we draw verticals at a regular interval on the throughout of this cross section. The distance of first vertical from the left bank is W1. Distance of second vertical from the first vertical is W2. Similarly, the intermediate verticals are at the distances Wi and Wi plus 1 from their respective previous verticals. The last vertical is at the distance of Wn minus 1 from the previous vertical, and the right bank is at the distance of Wn from the last vertical. The red dot which has just appeared on the first vertical is the point where we are going to measure the velocity, either by current meter or by any other method. Somehow, if you work out the velocity at this point, which is at 0.6 times the depth of vertical below the water surface, then the velocity at this point will be average velocity on this vertical. Similarly, on the second vertical, this red dot, if it is at zero point 0.6 times the depth of the vertical, then the velocity at this point again will be representing the average velocity on the vertical. If the depth of vertical is more, we can adopt two-point approach also. That means we have to measure the velocity at 2 points. First at 0.2 times the depth of flow, and second at 0.8 times the depth of flow along this vertical, and average of these two velocities is going to give us the overall average velocity along this vertical. Similarly, we have marked other points also, and after this we assume that we are having the average flow velocities along all these verticals. Now the next step is to divide the entire cross section into a number of segments using these vertical lines, the red dotted lines, which are passing through middle of the two verticals. So they are dividing this overall cross section into a number of segments, like this is the end segment on left hand side, this is the end segment on the right hand side, and a representative intermediate segment is shown in green color here. And what you will notice is that every segment is having one vertical in the interior of it, and we are having the average flow velocity that represents the flow velocity of this segment. The effective width W bar for the end segments is worked out by using this formula. On the left hand side, it is W1 plus W2 by 2 whole square divided by twice of W1. And on the right hand side, similarly, it is Wn plus Wn minus 1 by 2 whole square divided by twice of Wn. And for the intermediate side, the average width or the effective width of the segment is taken as half of Wi plus half of Wi plus 1. Now, how to calculate the discharge through each segment? So let us consider that delta Qi is the segmental discharge, and this is equal to area multiplied by the average velocity. Expanding it, it is delta Qi is equal to W bar multiplied by depth of vertical multiplied by the velocity of flow through the vertical. In this expression, W bar multiplied by depth of vertical is giving us the area of cross section of the flow, and the velocity of flow through the vertical is basically the average velocity as determined by the flow or the current meter. And the total discharge through the stream is taken as the sum of all delta Qi values. Here is the example. We have to calculate the discharge from flowing through this river from the following data. And the data is that distance from the left edge is given from 0 to 12 meters, and depth of all the verticals is mentioned from 0, 1.1, 2, 2.5, 2, 1.7, 1 and 0 again. So this represents that the distance 0 and 12, they are representing the extreme ends of the river, that is the two banks. Now, for working out the velocity of flow, number of revolutions of the current meter are given at 0.6 depth. So all these values are given as the number of revolutions for the current meter, and their duration of observation is also mentioned in the fourth row. To calculate the velocity of flow, the rating equation of the current meter is also given as V is equal to 0.5 ns plus 0.03. Ns here is the number of revolutions per second. So first of all, we have to calculate the first and the last segment. The average width of these segments is, by using this formula, it comes out to be 2 meters. And for the intermediate segments, we have to use this formula. Again, it is coming out to be 2 meters. Since the velocity is measured at 0.6 depth, the measured velocity is the average velocity along that vertical. And the calculation of the discharge are presented in the tabular form in this manner. Here the black columns or the text written in black is already given to you. This is the given data, and the red entries are incorporated by us. So like the distance from the from the left edge is given, and the average width is worked out that we have calculated in the very first step. Then number of revolutions per second is calculated as the number of revolutions recorded divided by the duration in seconds. So likewise, this entire column is worked out. Then putting this value of ns in the rating equation, we can work out the velocities. So all these values of velocities are worked out, and velocity when multiplied by the area of cross section, which is equal to average width multiplied by the depth. So the second column, the third column, and this velocity column, if they are multiplied together, we are getting the segmental discharge delta Qi from this particular column. So all these values are representing the segmental discharge through various segments. If you add them together, you get the total discharge going through the stream, that is 6.454 cubic meters per second. So this way, I think you can easily work out the velocity and the discharge going through the stream. Thank you.
Okay, students, now we will move into hydrographs. Now, before beginning the hydrograph calculations and lesson, I would like to play another video. Please watch this video as well. So after that, I will be talking about our form of calculations in hydrographs.
Okay, good morning. Let's get started. Today, what we're going to occurs to generate a hydrograph. It's the runoff from a water. It should give you.
Please watch this video. Then I will start my presentation.
All right. So a hydrograph, remember, is a figure that illustrates the runoff from a watershed in response to a storm. And there's this phrase in the textbook that I think is really important. This explanation of what occurs to generate a hydrograph. And you remember that I really nailed the like I emphasized the importance of understanding the relationship between lifting air and how it would lead to precipitation. This is kind of a general description of what causes runoff from a watershed. And the reason I emphasize it is just to kind of illustrate that the hydrograph begins when the abstractions, as this quote says, have been accomplished. I always thought that's kind of a funny way of putting it, that when the abstractions have been accomplished, then water begins to flow over land. And it kind of brings to mind the idea that there's this work or there's this obstruction in the way of overland flow, and it's the abstractions, the surface wetting, filling up the pores in the pavement, wetting the side of a building, wetting the leaves and the leaf litter on the ground. So once all of that's done, then we can see overland flow starting to occur. And there are a lot of factors that influence how high the peak is or how wide the peak is on a hydrograph, and we'll go over some of these individually today. And so if you compare the effect of slope, what you'll see is that on relatively gentle slopes where it's flat, the hydrograph shape is more spread out. The reason for that is that the velocity as it travels over the surface is going to be higher for a steep slope, and there's going to be relatively less of that diffusion effect that we talked about last time with the idea of pouring a cup of water into a flume and how it kind of spreads out the longer it's in the flume. So a steep slope leads to a higher peak, and the peak is sooner than with the gentler slope. In the case of hydraulic roughness, a surface that is smooth is going to tend towards a higher peak and a sooner peak, whereas the rough surface with, it's illustrated here with these big rock cobbles at the bottom of the stream, that's going to be slowing down the flow. And because it slows down the velocity of the flow, it also tamps down the height of the peak. If we have storage in the stream, meaning, for example, maybe in a regular cross section versus a relatively smooth cross section where there isn't any pools and ponds inside of the stream itself that have to be filled up before the flow goes down to the next pool or pond. If there's little storage, then the peak is faster and higher compared to if each of these little, in a way, they're kind of like detention ponds inside of the stream that have to be filled up before the flow occurs. And so this would be more akin to an engineered structure, an engineered channel, whereas this would be more natural structure or channel that hasn't been affected by human development. The drainage density is talking about how many secondary channels are feeding into the main channel in question. And so if you have a lot of small streams and it's very easy for the overland flow to get into one of those small streams, then the high density of channels allows the water to travel over the land for less of the time. And so as soon as the flow gets into the channel, it's moving with a higher velocity. But if the water is going overland, then there's going to be a higher roughness value, a lower velocity. And so a low density of channels means that more overland flow and a lower peak. And finally, the length of the channel has an effect as well, because even though the water is moving relatively fast in velocity terms, once it gets into the channel, there's going to be a delay and more of that diffusion effect the longer the stream channel is. And so you'll see that some of these are more pronounced than others in terms of the effect that it has. The hydraulic roughness in particular can really have a big influence on how big the peak is going to be versus how spread out it is for a rough channel, whereas in channel length, it doesn't have an enormous effect on reducing the peak height and delaying. And so all of these factors can be accounted for either empirically, or they can be combined together in a unihydrograph, which is what we're working towards discussing today. Here are just a couple of other considerations. If you think about the same amount of rainfall, but when in time it occurs, you'll notice that here you have a front-loaded storm where the intensity begins high and then it tapers off gradually. And what that's going to do is bring the hydrograph forward in time compared to a storm that is backloaded, where more of the precipitation occurs later than the peak itself is going to be later, because the abstractions are overcome very quickly in the case of this initially high intensity. You think maybe it's not going to have as much of an intense effect as it ultimately does, but these first few periods of rainfall intensity are just maybe barely enough to overcome the abstractions, and then we have to wait for some additional pulses of rainfall to come through before the hydrograph actually begins to take shape. And this idea of looking at when during time certain things occur, that's called temporal distribution. And so there's a difference between temporal distribution and spatial distribution. The spatial distribution is looking at where in space there may be variation in intensity. Temporal distribution is when during time is there variation in intensity. And so this next figure is an illustration of variation in spatial distribution. And so it's showing, for instance, that if you have storm A, which is just falling on a certain fraction of the watershed, that hydrograph is going to be not only lower, but later. Because what storm B does when the water's falling over the entire watershed is that the channel is becoming wet with the flow. Let me just point on the whiteboard here. So the flow that gets into the channel from here wets this segment of the stream, so that when all of the watershed is finally contributing, when the time of concentration has occurred and the entire watershed is contributing to flow, all of the stream has been wet in advance of that. Whereas in the case of storm A, it's just this one slug of water that has to first of all travel overland, and then as it's traveling through a dry channel, part of the flow is being stuck to the surface and lagging behind as it wets the bottom of the stream. And so there's a pretty pronounced lag and decrease in volume effect because only a fraction of the watershed had rainfall. And so depending on where your rain gauges are, if you had a rain gauge in the section of the watershed that is experiencing the storm, you may assume that it occurred everywhere. And so there can be a lot of variability that actually isn't seen depending on where you have your rain gauges. And so it may look like the entire watershed is experiencing a storm, but then if you were monitoring the outflow at the outlet, you'd be puzzled as to why you had such a small hydrograph compared to previous storms that were measured. And so you see nowadays increasing emphasis on radar being used to characterize the storm coverage rather than relying just exclusively on rain gauges that are at a single point. They're starting to use these radar cells, 2.5 kilometers by 2.5 kilometers, and trying to estimate how much precipitation there was over a much wider area and with a much greater resolution. This figure from the book kind of illustrates the effect of storm movement, and that is if it starts raining at A and the wind is blowing the storm towards B, so if the storm is moving away from the outlet, then what happens there is that it occurs much more soon than if the storm begins at B and is working towards the outlet. And so if the storm is beginning at B, then the rest of the channel hasn't been wet in advance. And if the channel is wet in advance, then it shifts it forward. But you'll notice that the amount is higher in the case of B to A because the rain is kind of following the movement of the storm as the water in the channel is moving downstream. So it's raining on top of that, and so it's kind of bringing it all together at the same time. So the peak is higher even though it's delayed. So these are just some of the physical effects that we have to ask when we're looking at storm data is, where in the watershed was the storm, over what time period, was it maybe even through the entire duration, or was it front loaded or back loaded? So these are important physical effects that will have a big influence on the hydrograph that you actually see. Rainfall excess is what's left over after infiltration. So this first figure is showing a rainfall hydrograph, and it's showing a graph of time and rainfall intensity. You see it's broken up into time segments. There's some variability in the rainfall intensity over time. This is the typical declining rate of infiltration. Why does soil infiltration rate decline over time? Why is it getting lower? Jeffrey? Okay, why not? Why when the ground has started to absorb water, why does the infiltration rate decrease? Suction pressure. Remember that the suction pressure is high. That potential attraction that the soil has for water is high when the soil is devoid of moisture. But as more of the voids get filled up, then the suction pressure decreases, and so then what's left to drive the soil downward is just gravity and maybe pressure from above, where the main effect early on was that the soil itself is drawing the water down. It's kind of sucking it down from the surface. So over time, what this is showing is the declining rate of infiltration. So anything above that curve we call rainfall excess. So it's the excess that's above and beyond the abstractions and infiltration. And so rainfall excess is what contributes to outflow from a watershed. We talked about why infiltration decreases over time. A hydrograph, remember, is a rainfall intensity figure, whereas a hydrograph is a runoff figure. Now, what we want to do is connect the dots between measuring rainfall, knowing how much of that rainfall is going to be abstracted, meaning surface wetting mostly, how much of the rainfall is going to be infiltrated, because the difference between rainfall and the abstraction and infiltration is rainfall excess. So we've talked about equations that you can use to estimate infiltration. Remember, there was the Horton equation, there was the Green-Ampt equation. So we have some numerical tools that will tell us this infiltration curve. And we talked about where you get rainfall data. You can get that either from a rain gauge or from an intensity, duration, frequency curve. So we have real-world sources of rainfall data. Rainfall excess is just going to be the difference between them. But what we need now is some way to predict what the shape of the curve that comes out of the watershed looks like. And the method we're talking about today is a unit hydrograph. And what a unit hydrograph does is it says, for a certain amount of rainfall excess, we expect a typical shape of the runoff out of this watershed. And if it's a big watershed, then the runoff hydrograph will have a different shape, characteristic shape, than a small watershed will. So here is a typical runoff hydrograph that's occurring from a unit of rainfall. And we call it a unit hydrograph because the idea is that if we have a certain amount of rainfall excess, whether it be an inch or a centimeter, we could prepare a relationship like this for any particular unit of rainfall excess. We want to know for a watershed in question, what does the typical curve of runoff look like? So you're assuming uniform coverage over the watershed. So it's not just for a certain part of the watershed that's having rainfall. You'd want to know if you had 1 inch of rainfall excess, meaning that you've accomplished, excuse me, coronavirus. If you have accomplished the abstractions and infiltration has been satisfied, so an inch of rainfall excess, what does the typical curve look like? The idea is that if you know what the watershed does for 1 inch of rain, then you can scale it linearly for 2 inches of rain. You just double the hydrograph. And I should be really precise as I'm speaking. If you know the response for 1 inch of rainfall excess, then you can linearly scale the response to 2 inches of rainfall excess. And so we're not talking about that the hydrograph isn't in response just to 1 inch of rainfall, it's to an inch of rainfall excess. And so it's just the stuff that's left over after all the other taxes, maybe you think of them, on the rainfall itself, the things that decrease the quantity of rainfall that's going to be running off. So there are some assumptions to applying this simplistic method. And with the unit hydrograph, you'll notice that we're assuming that the pulse of rainfall has a constant intensity during this unit of time and unit of depth. And we're assuming that it's uniformly distributed over the entire watershed and that the watershed isn't changing over time. And so to apply this unit hydrograph, you'd assume that there are no seasonal variations, which of course we know that there are. And so the way you correct for that is maybe you'd have a summer unit hydrograph and a winter unit hydrograph. You know, how does the watershed respond as conditions change? But if you have this unit hydrograph, it allows you to extrapolate from any kind of storm, regardless of duration or amount. Now, the thing that's a little bit tricky is when you do have a storm that is a longer duration than this single unit duration. So this might represent, it's saying here, 1 millimeter of rainfall excess, and let's assume that that's an hour of duration. What if you had a storm that lasted 3 hours of duration? What we would have to do is we would have to set it up with overlapping curves, and then the effect is additive in combining the watersheds together. So if there's multiple pulses of precipitation, we combine the responses. So you'll be given a certain amount of precipitation during a certain time period, and you'll know the unit scaling response, and we want to know what's the runoff for that one particular period. But then there's going to be precipitation from other periods as well. And so there's this figure from the book that shows the formula that would be used for a storm where you have 3 different precipitation amounts. So you'll notice there's P1, P2, P3. And then the U here is referring to what the watershed does during the first hour, the second hour, the third hour. So this formula probably doesn't make a lot of intuitive sense yet, but it will when we start doing things with the spreadsheet. You'll look at what's happening with the spreadsheet, and then we'll take another look at this figure, and I'll illustrate what this figure means. But the idea is that here is just a sample watershed. And these numbers, 1, 2, 3, 4, what this represents is the amount of the watershed that's contributing to the outflow in a given hour. So in the first hour, if it's raining over the whole watershed, in the first hour, it's only this area that is contributing flow at the outlet because of travel times. And so after 2 hours, then finally you're getting the water that fell in this region too. At the end of the second hour, that's contributing. At the end of the third hour, finally this area is contributing to the outflow. So these time bands are kind of working further and further away from the outlet. Now this is the response to what happens if there's 1 inch of rainfall excess in this watershed. So what this is showing is that if it rained over the entire watershed for 1 hour, so the rain duration is just 1 hour, and the amount of rain is such that there's an inch of rainfall excess. So there was more than an inch of rain. There was, an inch plus the amount that's going to be required for infiltration, plus the amount that's going to be required for abstractions. So there was enough rain that there's an inch of rainfall excess, and then what comes out of this particular watershed is this hydrograph. And so the time is more than an hour because the rain that falls all the way out here is going to take 6 hours to travel to the outlet. And so what we see, this 50 CFS, that's still the rain that fell during the 0 to 1 time period during the first hour, but it's taken so long to finally make its way to the outlet. So that's why we only see it at hour 6, is because of the lengthy travel times through the watershed. So just to say it one more time, this is the response to a storm that occurs in just 1 hour. From time 0 to time 1 is when the rainfall excess occurred, and then we have it draining the watershed over 6 hours. So the question is, what if we have a storm that's more than a single hour? What if we had a storm that in the first hour, there was 0.5 inches of rain. In the second hour, there was an inch. The third hour, 1.5, and in the fourth hour, 0.5 inches of rainfall. Then what would the hydrograph look like? And so that's what we're going to do with this template file that I've provided. So if you haven't already downloaded it in Excel, go get that template file, because what we're going to do is go through the process of creating a staggered unit hydrograph where there's an inch of rainfall excess that gives us this unit hydrograph, and then we know the precipitation amounts, and we're going to reduce them with the assumption that there are abstractions of 0.3 inches per hour. So just for purposes of simplicity, we'll set aside infiltration for now. We'll combine infiltration and abstractions together and assume it's linear, just so you can see the unit hydrograph part of it. Okay, so here is the student start file that we'll utilize. All right, so here it's reiterating that if you have an inch of rain, let's change this to make it so precise. Rainfall excess is what it's causing this. An inch of rainfall excess, the period was from 0 to 1, and that inch of rainfall excess was a constant intensity over the entire watershed, then this is the response that we get. And we're calling this U1, this U2, this U3, and those designations correspond to this kind of a figure. So it's not important to, just from the spreadsheet perspective, to label them. But when we go back and compare the results we get to this figure, I want you to know that the U1 is basically the unit response during the first hour, the unit response during the second hour, the unit response during the third hour, and so forth. Okay, so now here in this hydrograph window, we're going to transfer the data that we have in the problem statement. So time 1, 2, 3, and 4, we know the precipitation amount, and we're going to reduce out the abstraction to find out how much rainfall excess is left. So it's during hour 1, hour 2, hour 3, and 4. The precipitation amounts were 0.5 inches, an inch, 1.5, and 0.5. And for this illustration, we're just assuming constant abstractions of 0.3, but in reality, if you were doing this a little bit more sophisticated, what you're trying to do is apply the Horton method or the Green-Amp method and find out what is the declining rate of potential infiltration during each of these time periods. So you'd say, how much infiltration was there in hour 1 of the storm, in hour 2 of the storm. And you'd actually calculate the amount of abstractions rather than just using this placeholder constant value. So rainfall excess is precipitation amount minus the abstractions. So 0.2 inches during the first hour, 0.7 during the second, 1.2 in the third, and 0.2 in the fourth. So back to this figure that we're going to be looking at, P1, P2, P3, that refers to the precipitation amount during the first time interval and rainfall excess specifically. They use P just as the variable, but what they mean is rainfall excess. So rainfall excess during the second hour, rainfall excess during the third, and so on. Okay, now this is where we linearly scale with the hydrograph that we've got. So remember that this is what you'd see from an inch of rainfall excess. How much rainfall excess do we have during the first hour? During hour 1, we only have 0.2 inches of rainfall excess. And so what that means is we're not going to see 10 CFS during the first hour because the units here are CFS per inch of rainfall excess. And we only have 0.2 inches of rainfall excess. So the units here, 0.2 is rainfall excess during the period shown. So the way that we do this is equals the precipitation, the rainfall excess amount, and you anchor that reference, multiplied by the unit, and this is hour 1, so I'm going to go here to hour 1 amount, and that's what we'd expect. 2 CFS will come out because it was going to be 10 CFS if we had an inch of rainfall excess, but we don't have a full inch. We only have 2/10 of an inch. So does everybody understand why it would be 2 CFS? It's just a linearly scaled amount, and then we can drag that down, and you'll notice that we only have a response through hour 6. And so I'm going to drag that down through hour 6, and then afterwards it's just 0 CFS is coming from the watershed in response to this particular pulse of rainfall excess. All right, now here's where I start to see mistakes when I get quizzes and exams with questions like this, is that we need to stagger the time. Because remember, when does this rainfall excess occur? It doesn't occur during hour 1. This rainfall excess is occurring during the period from 1 towards 2. So we need to put in a 0 to begin with to stagger when it happens. But if it's 7/10 of an inch of rainfall excess, and we would have 10 CFS for a full inch, then we should see 7 CFS. But the 7 CFS occurs during hour 2. So it is going to be this rainfall excess amount, anchor the reference, multiplied by the unit hydrograph. But what you'll see is that the 7 CFS comes during the second hour because this rainfall was itself during the second hour. And then the watershed response to that occurs through the 7th hour, and then afterwards there's 0 CFS. Okay, so I'm going to pause the recording and give you some time to apply that same method for the 3rd hour and the 4th hour, and I wish I remembered to delete this formula over here. Total is going to be the combination of all of these 4 periods that are to the left. Let me give you time to work on that independently, and then we'll see if we all have the same runoff amounts. So for the 3rd hour, you need to put in 2 hours of delay and then begin the response of the pulse of rainfall excess multiplied by the response, dragging that down through the 8th hour. And then for the last, we have 3 hours where nothing occurs because this 0.2 inches of rainfall excess comes at the end of a sequence. So then in the 4th hour is when we begin to see the effect of that. And at first, it's going to occur over the area that's closest to the outlet. So the totals will be a combination of all of the pulses of rainfall. And so if we look here in the middle, this 385 CFS, what it means is that at a certain time, you're seeing the tail end of the first pulse of rainfall excess. The 0.2 inches of rainfall excess is mostly through the system. What we're seeing at time 5 is that contribution at the furthest part of the system. So if we look at the diagram, it's the rain that fell over here that's finally now just making its way to the watershed outlet, combined with the rainfall that the 0.7 inches of excess that is not as far through the cycle. You know, this is at the middle of the cycle, whereas this was at the tail end. And it's the combination of all of them. And so this figure that is showing the equation for it, what it illustrates is that the highest peak is going to be the precipitation that fell during the first hour acting over the further away area. So this is just saying area 4, the precipitation during the second time period acting over area 3, precipitation in the third time period acting over area 2. And so this formula for a runoff hydrograph is kind of built into the spreadsheet structure where you're adding it up. Each one of these cells is the effect of P1, U5, P2, U4, P3, U3, P4, U2. So the effect of the unit hydrograph with a 1 hour delay, 2 hour delay, 3 hour delay, and then you combine it all together. So that's the unit hydrograph method. And what it assumes is that if you know what a watershed is going to do for 1 inch of rainfall excess, then you can kind of predict what it's going to do for any other depth. And then if it's during one time period, then you just layer as many additional time periods with a staggered time delay after that. Any questions about the unit hydrograph method? So you'll use this for the homework assignment. There's a similar question in the example that we just worked through. Here's that same kind of formula that shows what you're getting for the runoff amount. In the case that we were just working, deconvolution is developing a unit hydrograph, and that's probably a little bit more intensive than we'll go through today. Instead, what we're going to take a look at is some information sources that you can use for your project. Remember, the research project, which I handed.
Okay, students, that video introduced you to hydrographs, and we will start doing the advanced calculations of hydrographs, how to separate the base flow and how to derive the hydrograph, then use superposition and S-curve methods in the next class. So I'll be sharing all this information. I think I haven't shared previous files, and I'm going to do it to Malshami so that she will upload everything into your classroom. Right, with that I will wrap up the class, and hope to see you next week. Good night.
Thank you, sir. Good
Good
night.
night, sir.
Good night, sir.